probably going to be quite a long session again this evening. I know that normally our workshops run for about an hour, but given the complexity of what we're trying to cover here, we don't want to restrict his expertise. So if at any point you've had enough of stats or coding or anything, and you just want to go home to your bed, that's fine. Just get up and leave. That's not a problem. Nobody will be offended.
Unless it's 5 minutes in, then I'll be offended.
But otherwise, I hope you enjoyed tonight's session again, and I'll hand over to Hayfen. So please welcome.
Thank you. So thank you for coming, guys. So last week we talked about some sort of introductory concepts in using R, and then this week it's going to be more about using R to do some of the kind of statistical analysis that maybe people are doing in Prism at the moment, so things like your t-tests, ANOVA, and stuff like that. Reasonably simple stuff, so not the kind of stuff that is going to probably convince you to use R over Prism. I mean, R comes into its own when you're doing sort of much more complex things, or when you're doing sort of bioinformatics or whatever, but it's good to know to be able to do the sort of basic statistics in R before you move on to the more complicated stuff. So, as I say, this time we're going to talk about some regression. Thank you. Regression, t-tests, ANOVA, that kind of stuff. Just a really quick to cover over a concept that we went over last time, which is about data structures in R, just to remind you that the two probably most important data structures when we're getting started in R are vectors, which are these guys, which is just, you can think of as a single row or a single column of data of a single type. And then the one which we're going to be focusing more on today, which we just finished with last time, which is the data frame, which is a structure for putting in the data from a complete experiment, the way that you might do if you were using something like Prism. So today, you're not going to need the R file that we used last time, but what we are going to do at the very beginning is create an R project file. So either you can open the R project file that you created last time, if you were in the previous workshop, by going to Project in the top right-hand corner, Open Project, and then look for the project file that you created last time, which should be in the same folder or directory as the data files, the two Pokemon files that we had. So what that will do is just tell R that its working directory is where your data is, okay? For those of you who haven't created one yet, I'll show you how to create one in a second. Okay, and if you did have an R file open, then it'll open that as well. If you weren't here last time and you haven't created a project file yet, what you need to do is make a folder and just put in it the two Pokemon data files that you would have received by email. And then once you've done that, click up in the top right-hand corner, New Project, Existing Directory, and just select the directory with the two Pokemon files. Does that make sense to everyone? Yeah? Basically, so that when we refer to a file by name, R will know which folder to look for to find that file. Otherwise, it'll tell you that it can't find it. So if you haven't got an R script file open, you can create a new one again by clicking R script in the top left-hand corner. So first thing we're going to do is reread in the Pokemon data that we read in last time, and we're just going to explore it a little bit with a few commands that we used just to recap from last time. So, and again, if you weren't here last time, if you start a line with a hashtag, any text coming after it is just a comment. It's just for you to read, and it's not read by R. And particularly if you finish a comment line with 4 dashes, then you can collapse your code and search for that section. So it's good to. So we'll comment our code as we go along. Okay, so we're going to create a data frame object called Pokemon. And just like we did last time, we're going to use the read.csv function to read in the file. So this function takes, in double quotes as an argument, the name of the CSV file that you want to read in. So let's do Pokemon.csv. Actually, I think it's a capital P, isn't it? And then hit Control-Enter to run the code. Has that worked from everyone? So if you now type Pokemon, it will just print out for you the entire Pokemon data set. Everyone has that? Any errors? No? Okay, so if you call the name of the data frame object, it'll just print out the whole data frame. And as it finds that it can't fit any more columns on, it'll squeeze the rest of them sort of underneath. So it's not very easy to explore your data by just looking at the entire data set. It's not very useful often if you've got a big data set to just have it printed at you, because you don't see all of the data and it's quite difficult to understand what's going on. So last time we talked about a few functions to understand our data a bit better. So the first one is the dim function, which if we pass our data frame to it, will tell us the dimensions, so that we know that we've got a data frame consisting of 251 Pokemon with 15 different variables. The head command is useful. This is the one, remember, that prints the first 6 rows from our data frame. The tail command, the last 6 rows. The str, which stands for structure, prints out a lot of information about our table. So basically telling us that it's a data frame of 251 observations, 15 variables, and it gives us the name of each of our variables, what kind of variable it is, whether it's an integer, factor, that's the only type we've got, and it tells you the first few observations of each one as well. And then finally we had the summary function, which prints out summary statistics for each of our variables. So for example, for hit points, we get the minimum, first quartile, median, mean, third quartile, and max values. So there are a few commands to just sort of explore your data frame and understand its structure and what variables you've got. Does that make sense? So your thesis is to catch all the Pokemon, measure everything about them, and then look to see if there are relationships in the data. So obviously we can get summary statistics and use these readouts to understand our data, but the best way of understanding your data frame is to plot your data. We're not going to spend a lot of time talking about plotting or explaining plotting in R, because R is phenomenal at making plots, and actually we could spend a couple of hours just talking about plotting. So we're going to create some plots, but I'm not going to talk about it in depth, if that's okay, sorry. But let's draw some plots of our data. So handily, the most simple way to plot a data frame is to simply pass it to the plot command. So if we supply the entire data frame to this function and hit Control-Enter, it might take a while on your computer, we get something crazy like this. So if you click zoom, it might make it a little bit bigger so that you can see what's going on. Basically, what the plot function has done, because we've passed an entire data frame, is plotted every variable against every other variable, which is often useful, actually, but in a data set as large as this, it's not particularly useful. So actually, let's refine our plot a little bit. Let's say, let me have a look at the head again. Let's say we only want to plot everything between HP and the type of Pokemon. So this is column 3, and this is column 10. So remember last time we talked about subsetting data frames with a square bracket nomenclature? So what we can do is, again, call the plot function. But this time, instead of supplying the entire data frame, we're going to say we want to supply Pokemon, all rows. So remember that what goes in front of the comma is for selecting rows, and what goes after the comma is for selecting the columns. So if I wanted the first row and the second column, I'd do that. Yeah, remember that? But if you want all rows, you just leave the row specifier blank. Now we want columns 3 to 10, so we could create a vector if we wanted to and go 3, 4, 5. But remember, there's a shortcut for doing that, which is simply 3:10, which produces a vector of the values 3 through 10. And now if we hit Control-Enter, it plots every variable against every other variable of a data frame that just consists of the variables between HP and type 1. Does that make sense? If we zoom in on this, all right, at least we can see a little bit more easily now what's going on. These kind of plots can take a little bit of time getting used to, but basically where the variable sort of name is, basically every plot below this, HP is on the x-axis, and every plot this way, HP is on the y-axis. Does that make sense? So, for example, this plot here is special attack on the x and HP on the y. Does that make sense how I'm reading that? So that's every variable against every variable. So you can look and see what different relationships there might be in your data to understand what's going on. Your PhD supervisor is interested in whether there is a relationship between the type of Pokemon and its attack value. So are you guys all right? Yeah. So instead, if we, again, call the plot function, and instead of supplying it just with a single data frame, it'll plot everything against everything, we can supply it with two variables. One variable to plot on the x, and one variable to plot on the y. So on the x-axis, we want, which is the first argument, we want the Pokemon data frame, we want all the rows, but we just want the type column. And that's type, capital T for type, and a capital I after the dot. That's going to be our x. So does everyone understand that that's going to be the type column of our Pokemon data frame? Yeah. And then the y, again, the Pokemon data, all rows, and the attack variable. And hit Control Enter. And this time, because R knows that the type variable is a factor, it's plotted it as a box plot, which is quite nice. You might find on yours that some of the labels aren't plotted because they're sort of too close to each other. But if you click on the zoom button again and draw it out, then all the labels should appear, or they should appear. All right, that one's not there because of the size of the screen, but does that make sense? Yeah? So this is all of our data. Let's say, for instance, that we are interested in comparing whether the attack values for psychic Pokemon are different from the attack values of rock-type Pokemon. So we might want to do a t-test. So if we close our plot, so the function for doing a t-test is handily t.test. And remember, if you write a function name after a question mark, it brings up R's help. So students t-test. And you can see in the usage that you basically, it accepts one argument called x, which is a numeric vector of data values, and y, which it says is an optional numeric vector of data values. If you're doing a two-sample t-test, then basically you give one group the vector values for one group, and then you give the vector values for the second group, and it'll perform a t-test between the two of them. If that doesn't make sense, we'll have a go at doing it. So let's create a vector called psychic, which just has the attack values of psychic Pokemon. So the Pokemon data frame. And remember last time we used logical expressions, so a way of extracting information or rows from a data frame that only satisfies certain criteria. So what we can say is take the Pokemon data set, but we want to select just the rows which satisfy the condition that their type is equal to psychic. And we want just the attack column. So does that make sense? What's going to happen? It's going to say, look at the Pokemon data set and select the rows for which their type is equal to psychic, and just select the attack column. So if we do Control Enter, if we then call our psychic vector, it'll print out the values, the attack values for all the Pokemon which are psychic. Okay? So let's create a second vector called rock. These are going to be our rock type Pokemon. and we're basically going to do the same thing. And actually, let's save ourselves some typing and copy and paste. And let's, of course, change this to rock. So it's going to look at the rock data frame and just select the rows which satisfy the condition that their type is equal to rock, and it's going to select the attack column. Control Enter, and then if we call the rock vector, these are the values of attack for the rock Pokemon. So like our t-test said, we've got our two vectors of data that we want to compare, and so it's simply a case of calling t.test and supply psychic as our first vector of data, and rock. And if you hit Control Enter, you get a nice output from our t-test. So it tells you what kind of t-test you'll run, and we'll talk about this bit in a second. It's a two-sample t-test, which basically means that you've got two groups that you're comparing. It tells you your data, your t-value, degrees of freedom if you care, and the p-value for your t-test. And then it gives you this little bit in English and your 95 confidence intervals and your means as well. By default, R performs a Welsh t-test. So if you've come to any of the other statistics workshops, remember that a Welsh t-test, not Welsh as in dragons and leaks and stuff, is a t-test that doesn't assume that your groups have equal variance. So if you were to just call t-test in R, you'll actually probably get a slightly different p-value often than you would in Prism. People say that actually there isn't any caveat to performing a Welsh t-test over a standard t-test. So R just defaults to doing the Welsh one. But if you really wanted to recapitulate results that you'd had in another piece of software, for example, you can call t.test psychic rock and then supply the optional command, which is optional variable, which is var.equal. So the variances are equal. Now by default, this is false. It doesn't assume that the variances are equal. If you wanted it to, you could say equals true. And if we run that, we'll see that we get let's open this up. We get a slightly different p-value between the two. So just so you're aware. Welsh t-test is better in most situations. It's better or as good as a standard t-test. So you might as well use the standard one. So if you don't care, then just leave this out. That was a two-tailed t-test, and most of the time a two-tailed t-test is the most appropriate kind of t-test. But if the difference in groups could only possibly go in one way, which doesn't happen very often, but sometimes, then you might want to perform a one-tailed t-test. So the difference between one-tailed and two-tailed t-tests. So if you wanted to perform that, again, t-test psychic rock, then there's an additional variable called alternative. And actually you'll find this down here. So by default, alternative is two-sided, but you can either stipulate that it be less, or so that the second group is less than the first group, or greater, so that the second group is greater than the first group. So if we say alternative equals greater, then let's do the other way around. Sorry, let's call it less. Then you'll see that your p-value is smaller, and in fact it's exactly half the size of the p-value here. Okay, and actually whether you use less or greater only depends on the order of which you put these around in the t-test. Does that make sense? Okay. If you wanted to do a paired t-test, so say you make measurements on something before and after some kind of intervention. So say, I don't know, maybe psychic Pokemon turned into rock Pokemon, I don't know. If we do, so basically the variable is paired equals true. If I run this, it'll give us an error and say that not all arguments have the same length. So if we find out the length of these two vectors, so remember this is the length function, the length of psychic is 15, but the length of rock is 13. So if we print these out, if you perform a paired t-test, it's basically comparing the difference between this and this, this and this, this and this, this and this. Does that make sense? But of course, once it gets here, it hasn't got anything else to compare it with, so it throws an error. So let's instead this is only for pretend, obviously you wouldn't really do this, but let's just tell it that we only want the first 13 values in the psychic vector. So basically we're just going to forget about the 90 and the 100 just for the sake of this so that we can perform the paired t-test. And if we do that, then it gives us our paired t-test and our p-value. T-tests, if your data are non-normal, then you might want to perform a Mann-Whitney U-test, which confusingly R likes to call a Wilcox test. So Wilcox.test, and then again, just like for the t-test, we supply our two vectors of data, psychic and rock. And if you hit Control-Enter, it gives you an error. Okay, we'll gloss over that. It might be because the sample size is quite small and that some of the values are the same as each other, possibly. I'm not sure. Basically, that's how you do a Mann-Whitney U-test. I'm sorry that it hasn't worked. If you wanted to do a Wilcox signed rank test, which is the non-parametric equivalent of a paired t-test, then just like doing a paired t-test, Wilcox.test, you supply your two vectors, but of course let's truncate this one to make it the same size. And then you just supply the argument paired equals true, and this probably won't work either. Okay. Oh no, sorry, I see it did work. It was above. Okay, yeah. Okay, no, so this is our Mann-Whitney U-test, and it does give a p-value. What the warning message is that it can't compute an exact p-value, probably because some of the values are the same and or your sample size isn't big enough. So non-parametric tests, if they can, will compute an exact p-value, or they'll approximate one depending on the size of your data. Sorry, the p-value was there. I didn't see it. And then the same for our Wilcoxon signed rank test. So we have a p-value for that as well. Does that make sense? Yeah. So, okay, so it gives you the p-value, but it gives you a warning message, and it basically says it can't compute the exact p-values, which means that what it's given you are approximations of the p-values. I'm not sure exactly why without spending some time looking at it. It might be that the sample size isn't very big, or that the samples are quite similar in position.
Mm-hmm. Let's say that we would like to do a paired test
Mm-hmm.
of a portrait location, like using 1 to 13. If
Mm-hmm.
I miss some value, can I tell the system to exclude the missing value?
Yes. So if
They have 13 and 15, but just because I missed some value in one of those columns. So I don't want simply to say 1 to 13. I would just say exclude the
yes.
missing one.
So if you've got missing data, the way that you should flag up missing data or code missing data so that R knows how to handle it is to give it a value of NA. So if, let's say, let me think. Let's just say we've got this may not work as. So we've got A and we've got B, and say we're missing a value for A and B, but we've got all the values for B. If you do d.test A, B paired equals true. Oh, okay. Hang on. Let's say, I don't know, 10. Oh shit. I'm trying to make the example work. So you'll see that it gives you the p-value and is quite happy. What it's done, and it hasn't explicitly told you, so it can be dangerous. What it's done is it's basically it's looked there and looked at the difference between those two. It's looked at the difference between those two, those two, those two. It's gotten here, seen that you've got a missing value flag, and so it's ignored that and therefore ignored that as well. So it just cuts off the comparison. Yeah, so the appropriate way to code missing values is with NA, because R knows how to handle it. Yeah, and it should do. Yeah, I mean there are certain analysis functions that you can tell R to handle missing values in certain ways, but that for the t-test it just ignores it. Okay, so we've done a t-test. Let's do some linear regression. So let's have a look. Let's plot, Pokemon. And also just remember as a recap, if we just want to plot an entire column of a data frame, we can just use the $ operator. So we give the data frame on this side, and then on the right side of the $, we give the name of the column. So we want to plot, we want to look at the relationship between attack and defense. So let's hit Control Enter. And now because we've supplied the X and Y coordinates, the X and Y axes as continuous variables, it draws a dot plot for us. So we're interested in seeing whether there's a relationship between attack and defense, and it looks like there probably is, and it looks like maybe there's a linear relationship. So the way that you plot a linear model, a linear regression model in R is with the LM function. So let's create a linear regression model object. Let's call it reg model, regression model. So the function to create a linear model is LM. And then you have to supply it with a formula. So we want to build a model where we regress defense on attack. Another way of saying that is we want to build a model where which would allow us to predict defense if we knew the attack of the Pokemon. So we'll put the def variable here. And handily, in this function, you don't have to supply, you don't have to say, Pokemon $def, because we'll give the data frame as an argument at the end. So the model is that def depends on, or is modeled by, so that's a tilde. So on a British keyboard, that's shift and hash. Has everyone got that? It's the approximate sign. So defense depends on attack, and the data is Pokemon. So that's what tells this function which data frame to look for the attack and defense variables. So once you've got that, hit Control Enter. And if we just print out reg model, then it tells us our call, so this is our model, and it tells us our coefficients. So if you've done much linear modeling, or if you remember doing linear slopes when you were in school, you remember that every straight line on a graph can be described by its intercept, so where it meets the y-axis at an x value of 0, and also the slope of the line. And that's what these are. So the intercept is 33. So what this means is that when a Pokemon's attack is 0, it still has a defense of 33. And the slope is 0.498. So what this means is that for every 1 unit increase in attack, defense increases by 0.498. If that doesn't make sense, or you can't visualize that, don't worry about this so much. But there is let's put it up here anyway. I'm not really going to explain this function, but there is a function to draw the regression line called abline. So you can type this if you want to, but don't worry too much about it. Okay, so this is the model that we've just fit to the data. So the intercept is 33. You see this value here is 33, and the slope is equal to 0.498. Okay, so that's our model, and it's useful to understand how, to build the equation that we could predict defense from attack. But actually, being addicted to p-values like we are, it's useful to be able to say whether our model fits the data better than just the grand mean. And the way that you can get a p-value for the slope is by using the summary command, like we did for the data frame. But this time, if you give it the model object and call control enter, then
one question.
Yeah, okay.
If the relationship between the two values aren't linear,
Mm-hmm.
will give you a different formula then, or a different model. I mean,
It'll fit the best linear model it possibly can by least squares. May not be a good model, so it's up to you to determine. And R is really good at doing non-linear regression modeling as well, but I'm not going to cover that today. Yeah. Sorry. Yeah, okay, yeah. I mean, don't worry about it so much because it's a bit of a complicated line of code, but it's basically abline. We pass it the regression model. This little dollar sign with coefficient 1 basically extracts the intercept. And then this coefficient 2 extracts the slope. And then we just say that the color is red and the line width is, or the line width is 3. So it draws a pretty line on our. Does that work? Is it working? Is it giving you an error, or is it?
Yeah.
What?
I'm checking just
Okay, so if you pass our regression model to the summary function, you should get an output that looks like this. So it tells us what our call is, gives us some information on our residuals, and then it tells us our coefficients and the p-values for our coefficients. So this first, so often in R, if you see PR, which stands for probability, of larger than, and this will often either be T or F or chi, this is the p-value, okay? The p-value for the intercept is basically just testing whether the intercept is different from 0, which sometimes is interesting, but usually isn't what we're interested in. This p-value tests whether the slope is equal to 0, and that's a very small p-value, so it's strong evidence that the slope isn't 0, and that therefore there is a relationship between attack and defense. Does that make sense?
So the attack will guide to the death. So will
Yes.
predict the death.
Yes.
So if you've got this p-value significant, then it will predict.
It will predict better than just the mean as a best guess. Yeah, and then it gives you some other information down here.
One more question.
Yeah.
When you say quest 1 and 2, do you always have to put 1 and 2, or you can play with those numbers? What does numbers mean?
It's in the abline
Yeah.
call. Okay, so basically what this does is this just selects this number, and this just selects this number. If you put them the other way around, this line would have an intercept of 0.49 and a slope of 33.47. So it's important to go around that way. I wouldn't stress so much about this line because there are much more powerful ways of plotting things in R than that way. Down here is your R squared, your multiple R squared. So basically what this is telling you is that 19.8% of the variability in the data is accounted for by the attack variable. The adjusted R-square is, so people use R-square as a measure of how well their model fits their data. But if you keep adding more and more predictor variables into a model, the R-squared value will always go up. And it might be that you're actually what's called overfitting your data. So the adjusted R-squared, you don't have to worry about it too much, but basically this penalizes you for having too many predictors in your model. If you don't care, well, that doesn't make sense, don't worry too much. 90.8% of the variability is being taken care of by the relationship between attack and defense. This p-value down here just tells you whether overall the model is better at predicting defense than the ground mean. And in this case, because we've only got one predictor, one linear predictor, you'll see that this is actually equal to the p-value for the slope. Again, if you don't care about that, then fine, don't worry. This one that's highlighted is important. It's important when you fit some kind of parametric model, whether it's a t-test, ANOVA, linear regression, to check the assumptions that the model makes. So if you came to the stats lecture before, you remember that one of the most important assumptions is normality of residuals. In Prism, it's actually quite difficult to do that without a bit of hashing. It's actually something that it's easier to do in R for once than it is in Prism. So let's make some room. Let's plot a histogram. Remember the hist function, and we're going to supply it with our regression model, and to extract the residuals, it's just the name of your regression object, the $sign as if you're taking a column from a data frame, and res for residuals. And if you do Control Enter, you'll find it'll plot a histogram of your residuals. So remember, by the way, let's go back. Remember that the residuals from your data are the distance between every single data point and the model that you fit. So in this case, it's the distance between every data point and the regression line. Okay, so the distance from here to here, distance from here to here. And one of the assumptions of a parametric model is that the distribution of these residuals is normal. So they should be normally distributed around this line. So if we look at our histogram that we just produced, doesn't look great. It looks actually like our data are positively skewed, where most of the data is piled up here, and we've got this long tail. Another useful way of checking the normality of your residuals, which we talked about in other stats lectures as well, which again is something you can't do in Prism, is by looking at what's called a QQ plot. And we can produce one of these by using the QQ norm function. And again, supplying it with our model residuals, which we get by giving it the name of our model, reg model, the $sign, and res, and hit Control Enter. Now what this has done is plotted every data point from our data along the sample quartiles and the theoretical quantiles that it should follow if it was a normal distribution. So basically, all of your data should fall along a diagonal. It's not always easy at first to tell, so for a bit of help, we can use the QQ line function, and again, supply it with the residuals from our model. And what this does is plot you, why is that? Oh, it's in black, okay, hang on. Let's make it red, so let's add an additional argument. Col for color equals red. Let me get rid of this. Oh, no. And actually, let's make it easier to see as well. Oh my word, hang on, no, that's not right. Sorry, you have to do the QQ norm plot first, and then the QQ line function. Okay, right, that's better. Right, does everyone get something that looks like that? Okay, so basically, if your data are perfectly normally distributed, if your residuals are perfectly normally distributed, they will follow nicely along this straight line. As you can see, our residuals curve away from the line, and they don't look very, very normally distributed. It takes a bit of time, I guess, getting used to seeing what is and isn't normally distributed.
Can we quantify it or just
So there are tests that you can use, and Prism will do them. The problem with them is that they're only good at detecting deviations from normality with large sample sizes. But if you've got a large sample size, then parametric tests are robust to violations of normality anyway. So actually, if you speak to a statistician, the way that they will evaluate normality residuals is by eye, which I know seems really sort of unscientific, but it's the best way that people do it. Yeah. Okay, so our model doesn't fit the data very well. So remember, one way that we can help make our residuals more normal is by transforming our dependent variable. So let's make a new model called regression model log. So we're going to log defense and see if that improves our model fit. So again, we're going to create a linear model. And what's useful is that you can actually perform mathematical operations on the variables within this model call. So what I mean by that is we're not going to regress defense on attack. We're going to regress the log 10 defense. Okay. So we've inside our linear model function, we put this log 10 function, and we've given defense. Is predicted by or depends on attack, and again, our data is Pokemon. Do you understand what's going to happen when we run this? So we run that. Again, we can let's just type. Let's print out the model. This time, because we've logged defense, the intercept is 1.5, and the slope of attack is much smaller. Let's do the same thing that we did before. Actually, let's plot the model so that you can see what's happened. So let's cheat and let's steal this plot function from up here. Oh no, other way around, sorry. So this time, this is actually the relationship that we're looking at. And again, let's steal this abline line of code, but this time this is actually regression model log, and run that. And so you can see that in our new model, based on the log data, our intercept is about 1.5, and the slope of attack is 0.004, which basically means for every 1 unit increase in attack, we have a 0.004 increase in log defense. Does that make sense? This is our new model. If we look at our p-value for the slope, so again, summary, regression model log, again, it gives us our formula call, and I mean the relationship is still significant. But if we have a look at how well our new model fits, let's have a look at the histogram of the residuals. So hist regression model log $res for residuals. That looks much better, a lot more normally distributed. And again, let's look at the QQ plot. So QQ norm, regression model log, and then just so that we can see how well it fits along the line, QQ line reg model log, color equals red, line weight equals 3. Oops, didn't like that. Oh, I forgot to tell it to actually plot the residuals. There we go. That looks a lot more better. That's what that's what normally distributed residuals look like. It's often the case that the very tails sort of come away because that's where there's not very much data, but that's normal. That's fine. Okay, so does everyone understand that we made a model of our original variables? It fits okay, but it violated the assumption of normality residuals, and then we fit a new model to the relationship between log, defense, and attack, and that sort of fixed that problem. Does that make sense? Okay, so let's move on to ANOVA. So we're going to take a subset of the Pokemon data, and we're going to call it Poke subset. So your PhD supervisor is interested in whether there are differences in attack between ghost, grass, ground, and ice type Pokemon. So you've got a situation where you've got a categorical variable with 4 levels and a continuous dependent variable. So let's just subset our data to pull out those kinds of Pokemon. So, take any row that satisfies the condition that Pokemon type is equal to, this is quite a long command, ghost, or, so remember the or symbol is the vertical line, which is shift, well, on my keyboard anyway, it's shift and backslash, creates the symbol that denotes or. If you don't understand this as we're going along, I'll go through it again in a second and explain exactly what's happening. Because it's a long line of code, let's make things a bit easier for ourselves. Remember, R is quite happy for us to split things across different lines. Or Pokemon type is equal to grass, or Pokemon type is equal to ground. Ground Pokemon were boring. Or Pokemon type equals ice. And then importantly, but easy to forget, is the comma at the end, because we basically want to say we want all columns. Okay, so has everyone finished typing that? Because it's a long one. No, sorry, that's fine. It's a long one. Let me know when you have, because then I will explain it exactly what's going to happen when we run it. If you have finished typing, try and work out what it's going to do. Oops, and I've got an intentional spelling mistake. Pokemon. So what's going to happen is I was going to look at the Pokemon data frame, and it's going to return every row which satisfies the condition the type is equal to ghost, or grass, or ground, or ice. So any Pokemon that is ghost, grass, ground, or ice will be returned. And we've asked it to return every single column because we haven't specified a column, so R assumes that you want everything. So if we hit Control Enter, and let's just call head on this. Oh, actually, no. Let's not head. Let's just call the whole data. The whole data. Oh no, actually, even better. Let's call just the type column. Okay, and if you hit Control Enter, you'll see that we've only got. Ignore this down here. We've only got grass, ground, ghost, and ice. So those 4 subsets. Okay. So let's just plot our data to have a look at it. Actually, don't worry about this bit because I'm going to type something that is maybe a bit confusing and isn't so important. You can follow along if you want to. It's just because the plot will look a little bit strange if I don't do this. And then all rows, type, don't worry so much if you can't follow along on this bit. Okay. So basically, we've got data that looks like this. We've got Pokemon that belong to these 4 categories. This is the attack variable, and we're interested in performing an ANOVA to see whether there are any differences between them.
In your example, there are Pokemon with several types, like 2 types of
Mm-hmm.
ground and ice, for example.
Mm-hmm.
And could you make a subset of Pokemon of both types? Like instead of or, have and?
Yes, you could do. The reason I didn't do it for this data set is because most of the Pokemon don't have a second type, so you'd get a lot of NAs. But yeah, you're right, you could. Yeah. Okay, so the way to create an ANOVA, perhaps surprisingly, is with the LM command, like we used before, linear model. So every parametric model, every t-test, regression, one-way ANOVA, two-way ANOVA, is actually based on the same equation called the general linear model, which we won't talk about today, but basically all of these models can be built from within the LM function. So we're going to make an object called just one way. This is going to be our one-way ANOVA. Oh, sorry, that's on-way. One-way ANOVA. And the model is a linear model, and we want to predict attack based on type. So this time, instead of providing a continuous predictor, we've provided a factor, and the data is poker subset. And hit control, capital P, that's it. Okay, and then if we call one way, we get some coefficients. So I know people are not used to looking at this for an ANOVA, but an ANOVA is actually a special case of regression. So you still get an intercept and you get slope values, but we won't really interpret them today. Most of the time, we just want a p-value out of our ANOVA. So if we, again, the same way that we did for our linear regression model, we use the summary function and pass our one-way model to it. Okay, this doesn't actually give us what I said we were after. So this actually tests each individual regression term. So this is actually testing whether ground is different from ghost. Let's ignore that because that requires a little bit of statistical knowledge to rely on. But what is useful about the summary command is that you get your R² value and you get your adjusted R² value, and maybe a p-value for the overall model if you wanted. But actually, if we want a standard, you okay?
Why we don't cost?
Okay, yeah. So in linear modeling like this, what is called the intercept is actually some kind of baseline group. It's usually the one that comes first alphabetically. Okay, so what this is, 52.5, this is the baseline value. This is the mean of the ghost group. The estimate for grass is the increase between ghost and grass, the difference between grass and the intercept. This is the difference between ground and the intercept. This is the difference between ice and intercept. So actually what these p-values are whether there is a significant difference between grass and ghost, ground and ghost, ice and ghost. If we want a sort of a traditional ANOVA table with p-values like we would expect to sort of get out of something like Prism, handily we just use the ANOVA function and we pass it our model. So this is a different way of thinking to how we do it in Prism. So in R, you create a model that models the data and you pass this into an ANOVA function. And if you hit Control Enter, then we get something that is a little bit more familiar. So we get the name of the factor, in this case there's only one, degrees of freedom, sum of the squared, mean squared, our f value, and then our p value. And actually, because we've only got one factor in this experiment, you'll notice that the p value for the type variable is the same as the overall p value. But if that doesn't make sense, then don't worry so much. So basically, this is our p value for the overall ANOVA. but of course we don't know exactly where our differences are, so we would use post hoc testing to find that out. Before we do that, let's evaluate our model fit like we did before. So we can plot a histogram of the residuals from this model. So the same way that as we did before, and hit Control Enter. That looks okay. There's a little bit of a lapse here. So let's look at our QQ norm. Doesn't look so bad. Let's have a look at, let's overlay the QQ line. All equals red. Oops. Oh, I put a full stop, that's why. That looks pretty good. That's not a bad fit. So I think we could be happy that we're satisfying the assumption of normally distributed residuals. There's another assumption, which is that the variance between our groups is equal. And the way that we can test that is using the Bartlett test. How many T's are in that actually? There's two, so Bartlett has 2 T's. And what we do is supply the outcome variable. Oops, sorry, that's not Pokemon, that's Poker subset. The outcome variable, and then supply the grouping variable, which is type. And then hit Control Enter. So Bartlett test of homogeneity of variances, and it gives you a p-value. And basically, if this p-value is small, then the variances between your groups are significantly different. So because this p-value is quite large, larger than 0.05, we can be happy that we're satisfying the assumption of homogeneity of variance between our groups. Does that make sense? Basically, that the variance of our groups is similar enough that it's not causing problems in our model. Okay. So if we found actually that our Bartlett's test was significant and our variances were very different, you can perform a Welch's one-way ANOVA, like we talked about in the stats lectures before. But you can't do that using the LM function. So instead, we can do this with the one-way test function, which you can also just use to perform your ANOVAs as normal. So again, we just provide our model formula. So attack, depending on the type, data equals Poker subset, and if we hit Control Enter, the default for, so one-way analysis means, and the default is not to assume equal variances. So this defaults to performing a one-way Welch's ANOVA. And you'll see that we get a slightly different p-value, 0.09, to what we did before, which was 0.06. If I did variances equals true, then we get the same p-value as we had before when we did the LM function followed by the ANOVA function. Okay, does that make sense? If our data are non-normally distributed, then the non-parametric equivalent of a one-way ANOVA is the Kruskal-Wallis test. And we can perform this doing Kruskal test. And it just needs, oops, I keep doing that, Poker subset, the dependent variable, followed by the categorical variable, the predictor variable. And if you hit Control Enter, it gives you a Kruskal-Wallis rank sum test and a p-value. Okay. So, did everyone manage to install the Mosaic package that was in the instructions? So, okay, has everyone got a Tinternet connection? Yeah. Okay, go to Tools, Install Packages, and type in Mosaic, and then click Install. and let me know if that works or not.
So just a quick question about
Yeah.
packages.
Mm-hmm.
Is the reason that requires an internet connection because it searches a database for and automatically downloads?
Yes, it does. So there's a thing called CRAN, which is the Comprehensive R Archive Network, which is basically when someone writes an R package, they upload it there, and it's sort of, it's checked properly. It's not just, you're not downloading from anywhere, and then it downloads the package, unpacks it, and installs it for you to use.
So all you need to know if there's a package that you want to install and you know what it is that you want it to do. All you need to know is the name of that package.
Yes.
Okay.
Yeah. Has that worked for everyone? So if you now type, and actually let's call this, let's call this post hoc tests. So if everyone now types library, so remember this is the once you've installed a package, the function to actually load it into your current R session is library and mosaic. You might get some text printed out, but you shouldn't get any errors. Has that worked?
But mine is still, so it says stop because it's still.
Oh, okay. Yeah. Okay. So let it run on. It's just installing the package. Okay. The reason that we're using the Mosaic package is that it comes with a useful function to perform a Tukey post-hoc test after a one-way ANOVA. So remember, Tukey post-hoc test compares every group against every other group. So I'll type this. I'll let people catch up. But in the meantime, the function is Tukey HSD, and the HSD stands for honestly, it's significantly different. That is true. And then you simply give it the name of your one-way ANOVA model. And if you perform Control Enter, it then gives you pairwise comparisons. So grass versus ghost, this is the p-value. For ground versus ghost, this is the p-value. So you can see that actually nothing is significant. Which makes sense because the p-value for the overall ANOVA was insignificant. Has everyone managed to get that far? Still doing it. Sorry. Okay, that's fine. That's fine. Only because time's going on. Do you mind if I move on a little bit and then okay. When it's ready, let me know and we can if you want to make if you want to use an adjustment method other than Tukey, so say you want to make select pairs of comparisons, there's a function called pairwise.t.test, and basically if you give the dependent variable as the first argument, you give the predictor variable as the second argument. Oops. Oh, I misspelt it. Oh, what? Oh, I misspelled that as well. See, this is why R is unforgiving subset. There we go. Okay. So be careful because these aren't paired t-tests. These are pairwise t-tests. So what it's done is t-tests between every one of these groups, and it tells you that the p-value adjustment method is what's called home. Which is a kind of post-hoc test. It's one of the best post-hoc tests actually for selected pairs. The reason I'm showing you this is because if you don't want to compare everything against everything, you want to do select comparisons. Probably the easiest way to do that is to tell R to do pairwise t-tests and tell it that you want the p adjustment, p.adjust dot method is equal to, turn it on my page, none. Hit Control Enter. And so what this has done is it's just performed t-tests between every pairwise comparison, and it hasn't adjusted the p-value. So you wouldn't report these p-values because, type 1 inflation rate, you usually correct the p-value by Bonferroni or something like that. But what you can do is, say we are only interested in...
What did you write after method?
So say it again.
After method, what did you write?
Oh, sorry. It's a long one. Let's move this over like this. None, yeah. Let's say we are only interested in the comparison between grass and ghost, these two. and ice and ground. So just these two comparisons. So there's a function called, oops, let's do it up here, called p adjust. So what this does is just takes in raw unadjusted p values and applies either a Bonferroni or a Shidak or a home correction to them. So we just supply it with a vector of p-values. So we're just going to select the ghost and grass p-value, which is 0.316, and the ground and ice p-value, which is 0.069. And we're just going to say method equals home. And we hit Control Enter. So what this has done is taken just the two comparisons that we're interested in and just adjusted the p-value for having made two comparisons instead of for having made 1, 2, 3, 4, 5, 6 comparisons. Does that make sense? Yeah? Maybe? So instead of so post-hoc tests adjust the p-value for the number of comparisons that you're making. So if you just want to make a couple of comparisons instead of 6 comparisons, rather than adjusting the p-values by whatever multiplier of 6, you can just adjust it by 2, so it's not as restrictive. Okay. Finally, I know time is going on. If you want to leave, I don't mind. I was just going to cover a two-way ANOVA before we finish. So, this is going to be another long line of code, sorry. Poker subset 2, we're going to create a new subset, similar to how we did it last time. So look at the Pokemon data frame, and select every row which satisfies the conditions. Pokemon, actually, tell you what, let's save some typing. Go back to where we defined Poker subset, and copy and paste. It'll save us so much effort. But the few things you need to change, call this Poker subset 2, the name of the object that we're creating. Change the first type to a bug type Pokemon, the second type to electric, third type to fire, and the final type to poison. The reason that we're creating a new subset is just because of the way that the data worked out. These groups worked out better for the next thing that we're about to do. So you can see that this time we're going to create a new data frame called Poker subset 2, and every row, every Pokemon whose type is bug, electric, fire, or poison is going to be in our new data frame. Okay. Now we're interested in whether okay. Again, don't follow along with this if you want to, but don't worry so much. It's just so that I can illustrate to you what we're modeling. Again, if this is confusing you, don't worry about following along with it. If you do, then fine, but if not, then don't worry. It's just to show you what we're doing. Okay, so you've been contacted by the RSPCP, which is the Royal Society for the Protection of Pokemon, and they're concerned that there are Pokemon in captivity suffer from lower attack values than Pokemon in the wild. So I think the Pokemon in red are captive Pokemon, and the Pokemon in blue are the wild Pokemon. And you're interested in building a two-way ANOVA model to see whether either type or captivity affects their attack. Okay, so our two-way model, as we're going to call it, again, we built it just the same way that you can build any linear model using the lm command. And we want to be able to predict or see whether our dependent variable attack is dependent on the type is our first one. Now, when you've got more than one predictor in the model, generally, if we're performing a two-way ANOVA, we want to test whether there are main effects of each factor. So there's a main effect of type and main effect of captivity, and usually we're interested in seeing if there's an interaction between the two of them as well. Yeah, the way to tell R that that's what you need to do is give it the first factor, the asterisk as if you're multiplying them together, and then the name of the next one. So what this will tell R to do is to ask, is there a main effect of type, a main effect of captivity, and an interaction between them? If you had an additional predictor, you could add that alongside and keep going as much as you wanted, okay? And our data is poker subset 2. And hit Control Enter. Oh, thank you, okay. Excellent, okay, great. If we print out our model, again, we get a lot of coefficients like our intercept and our differences for each of our coefficients. Again, if you're not so au fait with linear modeling, then don't worry about that so much. We're interested in p-values, really. So again, we can run summary of two-way. And again, we get p-values for each of these coefficients, which you may not be interested in. That's fine. We get an r-squared value again, adjusted r-squared value, which you can see actually has become a little bit smaller now that we've added another predictor, and a p-value for the overall model, which actually asks whether, for getting individual factors, whether the overall model fits the data better than just a grand mean. Actually, in this case, you can see that it doesn't, but we'll ignore that for now. And then if we want p-values for our factors and our interactions, again, we use the ANOVA command and supply our model. And then we get an ANOVA table. It tells us that our response is attack. We get a p-value for the type variable, which is insignificant. We get a p-value for captive, which is insignificant. And we get a p-value for the interaction between type and captive. So remember, this is testing whether the effect of captivity is the same across all Pokemon types. Does that make sense? Right, that's sort of as far as I was planning on going, but there is one other thing I wanted to mention. If people want to run off, you don't have to stay along for it. There are in almost all statistical packages like Prism or SPSS or SAS or STAT or whatever, when they perform their ANOVAs, they use something called type 3 sums of squares. R doesn't. R uses type 1 sum of squares. Okay, so this is a little bit complicated. If you don't understand, don't worry. Just be aware that it is different. So if you've got more than one factor in a model, so you've got two-way ANOVA, if all of your group sizes are exactly the same, whether you get your p-values by using type 1, type 2, type 3, or type 4 sums of squares, doesn't matter. The p-value is always the same. If you have unbalanced groups, so say you've got 5 Pokemon in one group and 6 in another group, the size of the p-value will depend on, if you're using type 1 sum of squares, which R does by default, the p-value will depend on which order you enter your factors in the model. So I will demonstrate. So our model originally was, let's call this two-way rev. Originally, we entered type 1 first and captive second. I know because I've looked, the group sizes aren't equal in this data set. So what I'm going to do is reverse these. And then get an ANOVA of so the p-value for type 1.
Can you show that?
Oh, sorry, yeah. Oops, wrong way. It's that one there. Okay, so when we put type 1 first, the p-value for type 1 is 0.15. When we put it second, the p-value is 0.16. Okay, so in this instance, it hasn't really changed much, and it hasn't changed the conclusion, but it has changed. When captive was second, the p-value was 0.68. When we put captive first, it became 0.53. Okay, so they're different. Type 3 sums of squares are completely independent of whichever way that you enter first, and they are the default type that is performed by Prism and SPSS, and they're the recommended type. Okay, so it's irritating that R does it differently. The way to get type 3 sums of squares in R might look a little bit scary at first, but it's not so complicated. Let's just do it, or try and do it quickly. Was everyone able to install the car package? If you didn't, it's Tools, Install Packages, CAR, which stands for Companion for Applied Regression, and let that install. And once it has, load it into your workspace by calling library car. Does that work for everyone? Or is it still installing? Don't worry. It's unfortunate that it works this way because it's one thing that makes two-way ANOVA, linear models frustrating in R. But basically, if you've got an unbalanced model, the way to specify your model to get type 3 sum of squares is, let's just call this two-way again. We can overwrite our model. Linear model attack dependent on type times captive data equals poker subset 2, I think. Yes. Okay, right. This is the bit that is a little bit maybe scary or complicated. It helps to have... Sorry, you okay? Yes, you just need it to be able to perform type 3 sums of squares. Yes. Okay. Yeah. It gives you an extra ANOVA function that gives you type 3 p-values. Okay. So for this next bit, maybe look a bit confusing. It helps to understand a bit more about the statistics to really understand the command. But if you don't care about understanding it, if you can just reproduce this, then it will work for you anyway. So you have to specify the argument contrasts equals, and for every factor, every predictor in your model, first you have to provide a list, which makes it seem even more complicated. For every predictor in your model, so for type 1, you have to tell it to perform contra sum, which are sum contrasts. And then we do the same for captive equals contra sum. Okay, and then when we're happy, we run this from the first line. And now we've built a model that the car package is able to use to give us type 3 sums of squares. The way that we then do that is by... and actually, let's copy and paste this, because I want to demonstrate to you that it actually doesn't... type 3 sums of squares are not affected by the order. So we'll call this two-way rev and overwrite the other one. And we'll flip these two round. So flip our predictors so that captive comes first and type comes second. Leave everything else the same. Now, the function that the car package provides for doing type 3 sum of squares is ANOVA, but with a capital A. And then we just give it our model. And then, again, there's another confusing thing. By default, this function will use type 2 sums of squares. But we want type 3 sums of squares. So we hit Control-Enter. And now we get an ANOVA table, and it says ANOVA table type 3 tests. And we get our p-values. And if we do the same thing, ANOVA, but this time on the model where we specified our predictors the other way around. Oops, rev. Oops. Oh my word, I need more. Right, there we go. Type equals 3. And if we run this, we find that the result is identical. Well, identical except for the fact that the order that they're listed in changes here, but the p-value for type is 0.15. Here it's 0.15. For captive, it's 0.88. For captive, it's 0.88, and the p-value for the interaction stays the same. So I'm sorry if that's confusing. It's unfortunately a quirk of R. Just be aware that if you're doing one-way ANOVA is not affected by it. T-test isn't affected by it. If you're doing factorial models, so 2-way, 3-way, 4-way ANOVA, if you don't have the same number of observations in every group, the standard R ANOVA function will give you different p-values depending on which way around you put them. I recommend just having a little Google about the meaning of the different types of sums of squares. But the default using, and the one that is recommended, that is globally accepted now as the correct p-value is type 3. It's just the fact that if all the group sizes are the same, then type 1 and type 3 are identical to each other. And then I did have a little section on running post hoc testing in 2-way ANOVA, but I appreciate that time is well running on, so if people don't want to hang on, then you don't have to. Or if you do, I can very quickly. There's one more package that you need. So let's call post hoc tests for factorial ANOVA. So there's one package that you need, which if you haven't installed, if you go to Tools, Install Packages, is called PHIA, P-H-I-A, which stands for Post Hoc Interaction Analysis. So firstly, I should mention that although this isn't the case in our data, say that the only significant p-value was that one of our factors was significant. The other one isn't, and the interaction isn't. You could just do a Tukey test. So say that there was a difference between these ones, these ones, these ones, and these ones. So just one factor. You could just do a one-way ANOVA because that just tests the levels of one factor. If you have an interaction, then you want to know usually, is there a difference between captive and wild for each level of Pokemon type? Okay. So if we load the PHIA package, does that work for everyone? And there's this function called test. Interactions. There's only two lines of code left in the whole workshop, I promise. Interactions 2-way. We supply this pairways argument. Yeah, so sorry, this first argument is the model that we're using. The second argument is pairwise, and we can supply the name of the factor in quotes, which is captive. I'll explain exactly what's going on when we run this in a second. And the next one is fixed, which is type, and then hit Control Enter. And now what this does is says, is there a significant difference between captive and wild at the level of bug? And then we get the p-values here. So is there a difference between captive and wild at the level of fire? So between these two. And this is our p-value. Does that make sense? By default, it uses the home post hoc test. But if you wanted... Well, so firstly, if you wanted to compare all the different Pokemon types at the levels of captive and wild, you could flip this around. So let's just copy this line. We could say, actually, we want pairwise to be type and fixed to be captive. And then there's we can supply this additional argument, which is adjustment equals, and we could say none to get just the raw t-test p-values, basically. And if we run this, p-value adjustment none, we get the difference between bug and electric at captive, and the p-value. We get the difference between bug and fire at captive. So we get a comparison between every combination of Pokemon type at each level of our other variables. So can you understand here that pairwise is type, so we're making pairwise comparisons between the Pokemon types at the fixed level of captive. So we're fixing the captive variable, comparing all the Pokemon types within that level, and then we're fixing it to the other level and comparing all the Pokemon types there. Does that make sense? Yeah? Okay. And that is it. That's all I plan on doing today. So So I'm sorry if the sums of squares bit was complicated, but has anyone got any other questions? So the reason that I put adjustment none is sometimes, like in this case, we would probably just be interested in comparing the captive versus wild for every bug level. But let's say you're actually interested in comparing basically every combination of data, so not just these, but also these. Or actually even, you may not be interested in comparing everything, you might just want to pick selected combinations. So like we did earlier with the one-way t-test, the way that you could do that is by doing selecting the p-values with no adjustment, just the raw p-values, and like we did earlier, passing them to this p-adjust command. So let's say we just want this one 0.3, 0.42 and 0.09, and we want to say method equals Bonferroni. There you go. So we've just taken the raw p-values just from those three comparisons and applied a Bonferroni post hoc test just to those. If you wanted it to do, so if I told it to do a Bonferroni correction here, the p-value adjustment would have been much more conservative because we're doing so many more comparisons that we're adjusting for. Does that make sense? Sometimes we're not interested in everything versus everything. Does anyone have any other questions? Anything not make sense? I mean, these are the kind of things that you can do sometimes, well, a lot of the time, easier in something like Prism, where R comes out on its own is when you're working with big data sets, doing complicated things, doing principal components, doing flow cytometry, doing bioinformatics stuff with gene arrays and stuff like that. But it's useful to be able to build simple models in R and do the kind of t-tests and stuff anyway that you use.
Okay guys, if we've got no more pressing questions, or if you're just too brain dead to actually think of them right
Probably.
now, then I'd like to thank Haytham for taking the time to actually give us such a thorough introduction to the software. So if you could all
Thank you.